the last thing I want to do today is go back and consider a new optimization problem. But it's an optimization problem involving exponential functions. Okay. And let's take a specific problem. Suppose you own a stand of trees. Okay. And over time, these trees become more valuable because the trees grow and they get bigger, and so they become more wood is more value. And let's suppose your engineers, your experts in plant growth, tell you that the future value of trees, V of t, is given by this formula right here. It is equal to, the value of the trees right now. You just planted them, let's say. Or alternatively, if you were to cut them down right now, they would be worth $1,000. Okay. Times e to the square root of t power. So the future value of these trees is given by this equation. This explains how the value of trees will grow over time simply due to the fact that they get bigger. Okay. Now, the question is, how long should you allow these trees to grow? The longer they grow, the more valuable they become, at least in the future. The future value grows with time. But should you let the trees grow forever? Because they do become more valuable with time. Should you ever cut down the trees? We want to convert this into a maximization problem. How are we going to convert this into a maximization problem? What are you really trying to, if you own the trees, what are you really trying to maximize? Not the future value, but the present value. You want to maximize the value of the trees in today's dollars. Because if you just try to maximize the value of V, there is no maximum. There is no maximum value of V, because as t gets bigger, they become more valuable. So you would let them grow forever. There would be no maximum value. Okay. But, Ben, if we're trying to maximize the present value of the trees, the value of the trees in today's dollars, how will we find that? What is the formula for the present value? Do you recall our formulas for the present value in the continuous model? The present value, let's call it A of t. A of t is equal to V times what? Ben, did you want to answer?
E to the negative RT.
Yes, e to the minus RT. If you want to maximize the present value of your investment, then it's just going to be V times e to the minus RT, and we're assuming continuous growth here. So R is the continuously compounded interest rate. Okay. It makes sense to use the continuously compounded interest rate here because this V, the future value is growing continuously. So you want to use the continuously compounded interest rate. So let's take a value for R. Let's assume that the continuously compounded interest rate is 10%. Okay, this business is used to doing investment projects that earn at least 10% rate of return. Okay, so let's assume that the continuously compounded interest rate is 10%. Oh, the discount rate, another name for it, yeah, the discount rate. So all we do is we plug in for V. The future value of trees is given by this formula right here that your experts gave you, your tree experts told you that trees will grow according to this formula. So that's our value of V. You just multiply this now by e to the minus 0.1t. And we can add those exponents and simplify this expression to be the following. The future value of trees is 1,000 times e to the square root of t minus 0.1t. And this is our objective function. This is the thing we want to maximize. We want to choose time so as to maximize the present value of the trees. Now, actually, instead of writing this as e to the square root of t power minus 0.1t, let's rewrite it as this. 1,000 times e to t to the 0.5 power minus 0.1t. Okay. So all of this is just the exponent on e. Okay. No, it's t. The square root of t is the same thing as t raised to the 0.5 power. Okay. Now, is that what you were asking, or were you asking a different question, Ben? Okay. Now, I don't know if I gave you this rule or not. When we were talking about exponential functions, one of the rules of differentiation is this. If you want to take the derivative of e to the f of t with respect to time, what is this derivative? Do you remember? If you have e raised to the f of t power, and you want to differentiate that with respect to time, what is that? Anybody remember that rule of differentiation? Yeah. Okay, close. It's f prime of t. You take the derivative of this exponent with respect to time, and it's f prime of t times e to the f of t. Let me give you a simple illustration of this. I know I gave you this rule. If you take the derivative of e to the t power with respect to t, what is that equal to? Ryan? That's just e to the t. So this is just a generalization of that rule. Notice you could use this rule, more general rule, because you could let f of t be t. If f of t is equal to t, then what is f prime of t? 1. So you could see that fits right into this rule, because if f of t is equal to t, this is just 1 times e to the t. But this is a more general rule. Okay. Let me give you a simple illustration of this. Suppose we have this. E raised to the t to the 0.5 power. And you want to differentiate that with respect to time. What is the derivative of this with respect to time? Well, in this case, what is f prime of t? Diana? Yeah, it's just a 0.5, or 1/2, as you said, times t to the minus 0.5 power, times times what? e, yes, t to the 0.5. Okay. Okay. In this case, f of t is just t to the 0.5. So here's your f prime of t times e to the f of t. You have to multiply that times e to the f of t. Okay. Well, that's what the rule we're going to have to use to get the derivative of a with respect to time. A prime of t, first order condition, is just going to be the 1,000 that's already there, the coefficient 1,000. Now our f of t in this case is this whole thing. Our f of t is equal to t to the 0.5 minus 0.1 t. So f prime of t is just 0.5 t to the minus 0.5 minus 1. 0.1, thank you. Yes, absolutely, 0.1. Okay. So we put our f prime of t in here, and that is 0.5 t to the minus 0.5 minus 0.1 times e to the f of t, which is just this. E to the t to the 0.5 minus 0.1 t. Okay. That is a prime of t. We set this equal to 0. Now, there's only one way this equation is going to be equal to 0. That's if this term, this expression within parentheses, is 0. Okay, you could divide both sides by 1,000. 0 divided by 1,000, still 0. On the right-hand side, you could divide both sides by this expression, get rid of this. So the only way this is going to be satisfied is if 0.5 t to the minus 0.5 minus 0.1 equals 0. Okay. Or we get 0.5 t to the minus 0.5 equals 0.1. Multiply, I don't like that 0.5, so let's divide both sides by 0.5. You get t to the minus 0.5 equals 1 divided by 0.1, which is 2. Another way, just multiply both sides of this. Multiply both sides of that equation by 2. This becomes a 1. This becomes a 0.2 over here. A 0.2, doesn't it? Not a, leaving off my decimals, aren't I? Okay. Now, if we raise both sides of this equation to, this is minus 0.5. So if we raise both sides of this to the minus 2 power, we would get t to the minus 0.5, raise that to the minus 2 power, equals 0.2 raised to the minus 2 power. And this becomes just t over here. Okay. So our t star value, or actually we should call it t sub 0, our critical value of t that satisfies the first order condition, is just 1 divided by 0.2 squared, or 1 over 0.04, or 25. So our critical value of t is 25. So you let the trees grow for 25 years, and then you cut them down. That satisfies the first order condition. But we have to do one more thing to be sure that this gives us a maximum. We have to check the second order conditions. And I'll leave it for you, since we're running out of time, I'll leave it for you to show, this is a little bit tricky, that the second derivative of a with respect to time is always negative. Or, let me rephrase that. It's definitely negative at the critical value of t. That's all we needed, for it to be negative at the critical value of t. Okay. And I'll let you work on this. We'll continue with this example on Friday. And we will have our last short quiz on Friday. Most likely something on logarithms.